I want to show you another challenge, and therefore I distinguish between two different types of electric drives. On the one hand side, we have often quasi-stationary drives, which are operated, as the name says, most of the time in steady-state operating points. This is the case if we think about typical industrial applications such as pumps or fans, for example. And these drives are characterized by the fact that the signals, if we take a look now at the inverter output in this plot here on the top, then you can see that during steady-state conditions for constant torque and speed, also the electrical signals are in a steady state, which means they are periodic signals. Of course, the voltage contains the harmonics of the frequency inverter. And if you would zoom in the current, then we would also see a current ripple, which includes switching frequency harmonics of the inverter. But nevertheless, these signals are nice periodic signals. And therefore, if we are interested in values such as active power, apparent power, reactive power, all power quantities, RMS values, but also fundamental quantities, then we can apply the well-known laws which are part of the standards. All of them are based on detecting the fundamental cycle of those periodic signals and then do evaluations based on this cycle. But if we go now to a lot of modern highly dynamic drives, for example, if we think about automotive applications or robotics, then these drives are characterized by the fact that they are typically not operated in one or only a few steady-state operating points. They are typically highly dynamic, which means frequency as well as amplitude may change frequently or even continuously, and we do not have steady-state operating points. And we have here on the bottom a picture of a startup process of such a machine. It's a no-load startup. This means we only need torque to accelerate the machine, and therefore torque producing currents, which you can see over here. But you can also directly see that these are not periodic signals or non-periodic signals. And of course, you can do a zero crossing detection in order to detect or calculate an apparent fundamental cycle. But as we all know, a fundamental cycle is only defined for periodic signals. So of course, we can do evaluations as we do it for the steady-state operated drives, but it may also lead to some misinterpretations. But what we can always do is we can calculate instantaneous values, such as instantaneous power, sample by sample. That's the reason why we need that and why it's so important to measure raw data, because then we can use the instantaneous power to investigate balancing processes, transients, or even subharmonics, which come from mechanical oscillations, all those things. And what we can also provide, this is also a part of a development in cooperation with Aschaffenburg University. We developed a highly dynamic power analysis method, which can also be used to analyze those signals. And it is not linked to the fundamental cycle of the signals, it's linked to the switching cycle of the inverter. And therefore, the power quantities can be calculated with a drastically increased update rate. That's a big advantage, but that's that only as a side remark so far, because today the most important topic is measurement uncertainty.